Hi, and welcome to Dragon Mathematics. I'm Dragon, and this is the mathematics. So today we're talking about polar coordinates, and what are those? Well, those are the coordinates that we've already used a little bit, right? When we're looking at an angle of 30 degrees, that is one of the coordinates. And then what we've slightly started to introduce is what if I had a radius of this size, right? Or a radius of this size. Okay, well that's going to be the r for radius. So if this is 1 and this is 2, this is 3, this radius here is 1, 2, 3. Length or distance, so a radius of 1.5 exists, and that's fine. Usually just use these integer values for an example. So for this point right here, that would be the coordinate at that point is 330 degrees. Or in radians, this would be pi over 6. Basic math class where you need to graph something or you care about points on a graph. Right, we're 3 ticks over on this x-axis, and we're 4 ticks up on this y-axis. Then we're at the point 3 comma 4, right? And so what we want to do is convert between Cartesian and polar coordinates. And so let's say, okay, well, what if this was on a circle, right? What would these coordinates be in polar coordinates instead of Cartesian? Well, it would be this angle theta and this distance r from the origin. Let's just get rid of that. Cartesian coordinates are useful for things like you have money versus time, you have a plot or a curve that don't have a periodic nature about them. Cartesian's good for that. And when you have something periodic, like say the behavior of a wave, right? We plotted sine like this. Well, the polar coordinate system is useful for tracking this behavior. If you're looking at something with radial symmetry or, a circle or some sort of spiral, right? If it's symmetric, you can apply a radius to it, right? And track the point on it clearly, then polar coordinates are good for that. It's good to know how to work with. It'll be important later. Polar coordinates are useful for analyzing certain geometries that appear in physics, engineering classes, and real life applications, right? Like electrical signals, 1 and -1, or between 0 and 1, we got a binary. And then smoother waves. You see waves all over the place. Light travels as a wave, water waves. Picture a plot with concentric circles, as this is called, right? You'll have radius 1, radius 2, radius 3. Here at this angle of, let's say, 45 degrees or pi over 4 radians, the point here is going to be in polar coordinates 1, 45 degrees, right? And the point here is going to be 2, 45 degrees. Here is going to be 3, 40. It's a little ambiguous here, but I'm saying this is this and that is that thing. Yeah, I remember from the trig we've been doing that here on the unit circle where r is 1, that same 45 degrees we just looked at, we've learned so far that the xy coordinate is root 2 over 2, root 2 over 2. Okay, in Cartesian coordinates on this same line right here, we'll learn in a moment, right? So this is cosine of theta, and this is sine of theta on the unit circle specifically, which is a radius of 1. So if you come out here to this radius of 2, the circle here, right? I actually have a highlighter now, right? On this circle, all you have to do to find the coordinates in the x and y of this, which I'm going to write over here because it's cramped, it's going to be r cosine of theta, r sine of theta, right? And the reason it works out for this one is because if r is 1, well then it's just 1 times cosine and 1 times sine. So at 45 degrees, on the radius 2 circle, the xy coordinates are 2 times root 2 over 2 and 2 times root 2 over 2. Right, and these cancel, so it just turns out that they're root 2 over 2, root 2 over or sorry, root 2, root 2. If I do, say, this concentric circle setup, I'll take 30 degrees. I like to use as an example. I'm just going to write it here so I don't have to be cramped. At this point, and this point, so r equals 1, r equals 2, our xy is, as we know, root 3 over 2, 1/2. Okay, both of those, right? And so these cancel. So what that's saying is that here, this is a height of 1 on the y-axis. So changing your coordinate system can help you analyze different geometries, different objects, different shapes, different behaviors. Depends on what system you're looking at. So this is how you would do it. X is equal to r cosine theta, and y is equal to r sine theta, right? And you can derive this from the way we identified cosine originally in previous videos. So if you do a little bit of algebra on this, you'll see divide this both sides by r and you have x over r, right? We determined that in a previous video. Divide by r, so y over r, right? That's how we get that. It's pretty simple. Going the other direction, so Cartesian coords to polar coordinates. My r is really bad. What happened to my r? Right, r is equal to the square root of x squared plus y squared. This should be obvious at this point, right? This is derived from on a right triangle that we typically find when we're dealing with our unit circle is this distance x, this distance y, this distance r. X squared plus y squared equals r squared. So if you take square root of both sides of these, then you have the value of r. For theta, it can be a little trickier. I'm going to say it's the inverse tangent of y over x. It can be a little weird. There are different cases. So this is true in the first and fourth quadrants. Let's do first and fourth quadrants. This will be the case. Remember that this is plus, plus, minus, plus, minus, minus, plus, minus. And I'm going to use 3, x and y being 3 and 4 as an example. So if you're given these in Cartesian coordinates, then you'll say, as we wrote up here, r equals x squared, square root of x squared plus y squared. And we'll substitute in what we know, which is 3, 4, which would be the square root of 9 plus 16, square root of 25, 5. Okay. So r is 5. That means that this radius, the radius of this circle is going to be 5. And then theta we want to find. If it's in one of these 1 or 4 quadrant, then we can simply use inverse tangent of y over x, right? Which is inverse tangent of 4 over 3, right? Which is something that we'll do in a calculator. And we're just going to get degrees out, but it depends what you're interested in. Inverse tangent of 4 over 3 is approximately 53.13 degrees. Okay, and I know that that's correct because it's in the first quadrant. These are both positive, positive 3, positive 4. First quadrant, it's correct. We'll look at the same example in the fourth quadrant. So if I had x, y, let's put a little break here. xy is 3, negative 4, okay? Then what's r theta? Well, r is going to be the square root of 3 squared plus negative 4 squared, which is just going to become positive. So again, we have 9 plus 16, right? Same radius, so we're not worried about that. Theta is going to be inverse tangent of y over x, so negative 4 over 3. Okay, let's put that in the calculator. Inverse tangent of negative 4 divided by 3. So what we get is negative 53 degrees, right? And so that also adds up. If I had in this circle here, I'm going to erase the quadrants now. In this circle, if I have 1, 2, 3, 4, 1, 2, 3, 4, right? 3, 4 on the circle is going to be right there. Okay, and so this angle, what we calculated is 53.13 degrees. That's great. And then if I go 1, 2, 3, -4, so 1, 2, 3, 4, 3, right? This point is going to be, do this, -53.13, right? And we just need to remember that a negative angle is going to be equivalent to this angle right here is the same as saying this angle right here, right? Those are going to have the same point on the circle in XY coordinates. But now let's go to the next example. So let's say we want to do something in quadrant 2, which would mean xy equals -3, 4, right? Because remember, negative, positive. So say I want to do the same thing, but in quadrant 2, -3, 4. Well, I can tell you r is going to be 5 again. You can check to see if I'm right. Theta is going to be, or at least I'm going to try, but I need to show you how we modify this for the second and third quadrant. But let's put a question mark here to be thorough. Is this true? If I do inverse tangent of 4 over -3, what do I get? I get -53 degrees there. Now we have to ask, does that make sense? Here at -3 on the circle, -3, 4, is this angle, so we're going negative, is that -53? It doesn't look like it, right? So what we actually have to do, so we're going to say no, it does not equal that, and so no, we should not use that. What we need to do is theta, I'll put a little subscript here, theta in the second quadrant is going to be equal to inverse tangent of y over x plus 180 degrees. Or if you're working in radians, plus pi. Okay, so we're going to test that. Remember, we got -53.13 degrees. Well, let's add 180 degrees to that. And now we have 126.87 degrees. And the question is, does this look like this angle? Does that look like 126.87? It does, right? Because this is 90, this is 180, 126 is approximately in between those two. Okay, good. So then what if we have the third quadrant? xy equals -3, -4. So r is going to be 5 again. You can check. Theta is inverse tangent of y over x plus pi. Let's do it in radians because it's good practice and radians are useful and common. Well, let's test that. Okay, so inverse tangent of -4 over -3. See, that's going to give us 53 degrees. This point in quadrant 3 down here, right, is not going to be 53 degrees, right? It's going to be, let's add our, I'm sorry, I promised we would use radians. We'll do both. Let's add 180 degrees. So I'm not going to write it, but 233 degrees looks much more correct because you'll know this is 270, this is 180. That makes a lot more sense that 233.13 degrees would be in there. But I promise you would do it in radians, so let's do that. Inverse tangent of -4 over -3. It's going to give us 0.92 radians, right? Again, we know that that's wrong because this is 1.5 radians, this is 0 radians. It's telling us again that without the modification that we need to do would be somewhere in here, right? 0.92. And that's not what we want. What we want is once we add our pi, so let's just do add pi. So the radians answer is 4.07, and this definitely looks like 4.07 because, again, if I modify this for radians, it's 3.14. This is 4.5 or 4.7. I always forget. 4.71. So this makes sense that it would be in there. This is approximate. Okay, so to recap that, because I know it's kind of weird, going from Cartesian to polar coordinates, we do this. R equals the square root of x squared plus y squared, right? Theta in the first or the fourth quadrant equals inverse tangent of y over x. And theta, when you're dealing with the second or third quadrant, is equal to inverse tangent of y over x plus pi, or if you're in degrees, of course, for x plus 180. Cool? Okay, so this isn't really a complicated video. We're just gonna do examples of just that, converting. That's the main thing you're gonna do in a trig class. It's important to know these things because, converting between the coordinates, if you're looking at the x and y at any given point, right? This has an x and a y, right? This is the x and this is the y. And it's just sometimes easier if you have something that's on a circle, if you have a system that's periodic, your calculations are going to be easier to do if you're considering, a rotational basis, right? You want to think about it more like this: theta 1, theta 2, right? So your theta is increasing, and in this circumstance, your r would be staying the same. But like I drew the spiral, if you have something like this, oddly, well, you would be dealing with a theta that's constantly changing, right? And you would also be dealing with an r, a radius here, that is also changing. In this case, the r is increasing this way, right? So once you master polar coordinates, eventually you'll be concerned with spherical coordinates because we live in a world, believe it or not, that's three-dimensional. And, we live on a 3D sphere, oblate spheroid called Earth. And in order to get to this, in order to get here, you have to first master 2 dimensions. All right. And a lot of calculations are done in 3D because we live in 3D. So it's very important to us. Okay. So let's do a problem. Problems. These shouldn't be too hard. We'll do convert xy to r theta, where xy is 1, 1. Okay. R is the square root of x squared plus y squared, which is 1 squared plus 1 squared. We take the square root. That's going to be the square root of 2. So I know my r. And theta, we know how to do that now, but I have to first do a check. Okay, 1, 1 is in the first quadrant, so we're going to be good without the modification, which means we can do this in the calculator. Inverse tangent of 1 is 0.785 radians. We'll just do 0.79 radians. And so r comma theta is square root of 2 comma 0.79. You don't really have to write the rad. I've just been writing it to be clear. But again, it's very circumstantial when you're going to care about degrees versus radians, so I can't tell you which one to worry about right now. If you are in an early on class, you're going to be using a lot of degrees. And if you're in an early physics class, you're also going to be using degrees. Then if you're in a later physics class, you're going to be using radians. So it just depends. So there you go. And we'll do another one of those. Let's see what I do. So we'll convert this where xy is 0, comma minus 3. So I've given us something interesting to deal with here because this will cause something to pop up. R is going to be the square root of x squared plus y squared, and that'll be square root of 9, which will be 3. And then this is sort of interesting, right? Because here, if I just look by inspection, I can see, okay, the x value is 0, so the distance left and right is 0. The y is negative 3. So if I have a hypothetical circle at this point, then if you ask what quadrant is this in, right, it's not really in one. It doesn't make sense. Well, that's interesting because the answer to theta also doesn't really make sense here. So it's a good thing we have a problem like this to check this. Y is negative 3 and 0 is going to be in the denominator. Well, we already know if you try to do that, it's going to be no solution, whatever way you want to write that. And so what I say to do is just think about it. Again, if you were to just look at the Cartesian coordinates that we start with, x, y, here's negative 3 down here. That's where the point is. So here's the origin, here's our point. Here we solve for r. right? Which gave us 3, which makes sense, right? At -3, the radius is 3. Over here at +3 in the x, the radius is 3. At y equals 3, the radius is 3. And at x equals -3, the radius is 3. So that's logical. And then we want to find theta, but we don't really know what to do with -3/0. The reason it works out that way is because inverse tangent is based on the function tangent, which is based on a tangent line, which says at this point on the circle, if you have a line, right, it makes sense to call this tangent. A line where its slope is perpendicular to the face of this circle here. I'll just write it like this. If you take the slope of this tangent line, that gives you the information about what the function tangent results in. And so this is some arbitrary, 45 degrees or so. But what if we were to look at, I'll do an example here. The tangent at 0, right? Well, the coordinate here is x, y equals 0, 0 in Cartesian coordinates. And the slope of this line, see this says some sort of slope. It's a negative slope going from left to right. It's a downward slope. This has a slope of infinity, right? Because it's not sloping down to the right. It's not sloping up to the right. It's sloping so fast that, the point of slope is if you have, what do we use? A skier, person skiing. My drawing is not going to be really great today. If you put a person skiing on this slope, what's going to happen to him? Well, he's going to go down. Right? So that's what makes the slope negative. And then if you put the same skier on this tangent line, right, he's not going to make it. He's not going to go up. He's going to slide back down. But, he'd have to climb. It wouldn't be a skier. It would be a rock climber or something. That's what makes it positive. And then with this case, it's like asking, well, what if I put a skier on here? What's going to happen? I mean, he's not going to go left or right at all. Or they're not going to go left or right. It's just gonna accelerate to terminal velocity so fast and just really, fall as fast as possible. There's no friction. They are not really even on this line. It doesn't make sense. It doesn't matter if the line was there because it's straight up and down. So his movement is not really influenced by it. Then here, in our case for this problem, so I can finally get to the point, what if you have a tangent line like this? You say, what's the slope of that line? It has no slope. So what can we do with the line that has no slope? Well, clearly, this is why we're getting an issue. We're having an issue in the functions because it relies on the slope of the tangent line to tell you what the solution of the function. So there's no solution, which means, long story short, I guess, is I would go here and I'd say, well, we know this. It's 270, right? So if you get any of these, what is this? 180. If you have either x or y equal to 0 in your Cartesian coordinates, it's going to be one of these 4 points. And we know them by heart. Right, this is 0 pi, this is pi over 2, this is pi, this is 3 pi over 2, 2 pi again. So that's kind of the cheater method because there's nothing I can do with I can't just use the hard-coded inverse tangent of y over x in this scenario. So I'm glad we got that example because it kind of allows us to deal with that. So r theta for this is going to be 270. I always like to write both. That's radians. Okay, so we'll do one more. This one I'll do a little quicker or more quickly. XY is -5, 0. So you can do a sketch. I like to sketch things out. Just think about it. If my x is here at -5 and my y is 0, so this isn't going up and down, I mean, I already know what theta is. It's pi, or 180 degrees. And I already know what r is, right? If I had -5, this is a hypothetical. If it was -5 and even this, then I can't say that for sure. I'd have to do a calculation. But if it's 0 up and down and -5, aka 5 units to the right or the left, aka 5 units to the left, then the radius of the whole circle has to be 5. So the quick way through this is to say this is 5 comma pi. Okay, if you want to do it the rigorous way, we'd say r is equal to -5 squared plus 0 squared, and all of this is under the square root. So the square root of 25 is 5. Then let's say inverse tangent of y over x equals what? Well, what if we do inverse tangent of 0 over -5? You already know what that's going to give. It's going to give 0, and inverse tangent of 0 is 0. So this would say that our angle is 0. And so if you get that and you sketch this, you'll look and you'll maybe go back to your notes and say, wait, what happened? Did I do something wrong? Check your calculation, whatever. But as we spoke of, if something's in the second or the third quadrant, we're going to add pi. And this, though it's not clear whether it's in the second or third quadrant, right, because it's right here on the x-axis, it's definitely within the second or third quadrant. So I should have been clear earlier. It's anything from here to here. Okay, so 0 plus pi, that gives us pi, which, like I said, you should be able to figure that out just from looking. That's 180 degrees or pi. All right, good. So that's Cartesian to polar. Let's go polar to Cartesian problems. So number 4, we'll do convert this to this, where r of theta is 2 pi over 6. And remember I said that x is r cosine theta, y is r sine of theta. So it's just really plug and play, right? So for our example, r is 2, cosine of theta is cosine of pi over 6. And again, you can either use your calculator if you're allowed to, or you can remember that 30 degrees or pi over 6 is here. This is root 3 over 2, 1/2. And so that's on the unit circle, right? On the unit circle, it's root 3 over 1/2. But the radius of our circle, as we were given right here, is 2. So it's 2 times that value. So 2 times root 3 over 2. And this one will be the same thing. 2 sine of pi over 6 is equal to 2 times this sine, 1/2. So it's 1. And this is what? Square root of 3. The answer is root 3, comma 1. And again, to clarify that, to show what we're talking about there, it's just to say that you have this circle, your unit circle, the angle pi over 6 right here. It's the same as 30 degrees. And then we're just asking, okay, well, what if it was the next circle? We just kept going. We kept the angle, so still pi over 6. But out here, well, it makes sense that this point would be square root of 3, 1. Then you could just keep going indefinitely, really. I mean, the next circle out, I'm going to say, would be 3 times this. So that would be 3 root 3 over 2, and 3 times 1/2, which is that. You keep going, right? 4, 5, 6, whatever the radius of the circle is, you're just calculating that radius times cosine of the angle, which the cosine of the angle is going to be the basic values that I told you would be important to memorize, right? This one, this one, this one, times the radius if you want to know at each concentric circle. Okay, so another example of that, polar to Cartesian, we're given r theta equals 3 to 70 degrees. I think I just did this in the other direction, but that's fine. And we want x and y, so x is r cos theta equals 3 cos 270. Y is r sine theta equals 3 sine 270. Okay, this is 270 here on the unit circle. Cosine of 270 degrees is this x value, which is 0. Sine of 270 degrees is this y value, which is -1. So x, y equals 0, -1. Which makes total sense. This is y. There's no x distance, thus x being 0. This is -1. And we learned that, right? This is 0, 0. This is 1, 0. This is negative 1, 0. Sorry, 0, 0. This is 0, 1, negative 1, 0, and 0, negative 1. Okay, so like I said, it isn't that intimidating. It's just important to learn the basics of converting from different coordinate systems. And yeah, it'll help you in the future when it comes to a problem where you, again, say that you found a point here, and you found a point here, and then you found a point here, and you were just thinking Cartesian wise. Well, you might do an experiment and take more points and determine, oh, look, these are all in the same circle. And to do that using polar coordinates is going to work much better. It's like saying if you have if you have some sort of system, like you have this pendulum, right? Say you have this pendulum, it's going to go swing back and forth on here. This angle theta is going to continue to change. You're going to have theta, then you're going to have negative theta, right? Well, what if you weren't using theta and you wanted to track the motion of the pendulum along this swing, and you were going through and you were like, okay, so what's the y coordinate here? We'll say is like 2, then the y coordinate here is 3, the y coordinate's 4. All right, and the x, well, the x in that circumstance, it's going to come out to would be say like 1.23211. The x coordinate here is now 2.92241, right? You're going to spend all this time, say this is x equals, and where are we at, like 7.1411612. It's just ugly. And then you just one day realize, oh, well, if I were to just look at the radius, right, the distance from my origin up here, my fulcrum point, to the pendulum, the mass of the pendulum, if I just look at that and then I look at the angle that that the pendulum makes with this original zero line that we created, if I just look at the different thetas, I can tell you this point by just saying, what's r? Again, let's make up an r, and I'll say what this was 1, 2, 3, 4. So let's just say this is 10. If this distance from the ceiling to the mass of the pendulum is 10, well then the point at anywhere on this swing is just going to be r times cosine of whatever angle you have. So you find, sorry, the x will be that and the y will be that, right? So you just change your coordinate system into polar because it's a way to look at it that it's just going to be so much easier to manipulate, so much easier to pull answers out of. So at any point here, if you want to know how far left and right the pendulum is, well, you just have to look at r, which is 10, times cosine of, say, right, like right here, say that's a 30-degree angle, and drew it too long. This point, the pendulum is now at 10 cosine 30 degrees. You can plug that into the calculator to get the exact x value if you want, right? Then you want to know, oh, how high is the pendulum off of the bottom of its swing, its equilibrium point? Say it's all the way up here. Well, this distance right here, it is y, but it's also r, which is 10, times sine of whatever this angle is that it makes, right? Say it's a much bigger angle. It's not yet 90, but it's, say, 80, right? You know the height and you know the left and right motion of your pendulum just by plugging these into your calculator, rather than by freezing it and counting the ticks that are going to end up being insane decimals, right? What's 10 times sine of 80 degrees? Sine of 80 degrees is a height of 9.848077753, right? If you go to every point on here and you're writing those down, it's much less precise, it's much less convenient. So the end of my rant, the point being, this exact height, right, h I wrote, is much more convenient to work with. And with a pendulum, you're going to care about the height because, well, the force that is causing this pendulum swing to happen, right, is gravity. And the potential energy is influenced by the height and gravity at any given time. And so that's an example of where you would use it. So I hope that helps. and I'll see you in the next video. Bye-bye.